Hello, everyone. Thank you so much for joining us. This is the fourth installment of our summer faculty lecture series. My name is Christoph Rede. I am the president of the Williams-Boston Association, and on behalf of the WABA, I'm delighted to welcome everybody to this virtual event. We're really excited to see a lot of alumni and parents joining us from around the country, in addition to all the EVEs from the Boston area. These one-hour virtual lectures are scheduled every 3 weeks, and they showcase Williams professors from across a range of academic fields. The previous lecture was given by Sam Crane, political scientist, and he spoke about the complicated relationship between the USA and the People's Republic of China. The next lecture in the series will be by music professor Zachary Wadsworth, who will be talking about music and film, and that's going to be on September 3rd. And rounding it out for the last lecture will be political theorist and chair of African Studies, Neil Roberts, who is going to be speaking about living free in an age of pessimism. So please keep your eye out for updated announcements about those talks that should be coming from Alumni Relations in the near future. Just a quick note for housekeeping, the chat feature is on, and as you saw the message, you are welcome and encouraged to come and introduce yourself in that chat box. If you have questions for Professor Bradley during the talk, the best way to submit those is using the Q&A feature, which should be at the bottom right corner of your Zoom window. And Professor Bradley will go through those questions after finishing her presentation. There's no need to wait until the end of the talk. You're welcome to submit questions as we go along. So with that, I'd like to welcome and introduce Alice Bradley, Assistant Professor of Geosciences at Williams. Alice is a climate scientist with research interests focusing on Arctic sea ice, measurement methods and instrumentation, and global governance of observing systems in the Arctic. Professor Bradley teaches classes on weather and climate, environmental observation, climate modeling, and the cryosphere. She holds a PhD in Earth and Space Remote Sensing from the Aerospace Engineering Department at the University of Colorado Boulder, and a BE in Electrical Engineering from Dartmouth. Alice, thank you so much for joining us today and taking the time to speak with alumni and parents. And with that, I'm going to turn it over to you for today's talk entitled Cold, Dark, and Violent, Measuring Sea Ice in a Changing Climate.
Thank you, and thanks for that introduction. I will say I will encourage everyone to please use the Q&A box liberally. Having gotten used to teaching at Williams, if I go more than 5 minutes without answering a question, I feel like I'm doing something wrong. So my talk today is about really how we measure sea ice in the Arctic. It is in many ways a whole different world than what we experience in our day-to-day here down south. And so the way we need to approach problems and the way we approach making observations is very different. So my talk today is very briefly outlined as starting with sea ice, talking about climate, and then how we get into observations and measurement technologies. And this is really where I've been working with students at Williams on some of these new projects. So we'll get through the first two, and then I'll take a break for kind of wrapping up questions at that point, and then get into the measurement side before we finish. So the Arctic is a very fuzzy concept. There are many, many definitions, some of which conflict with each other for high Arctic, subarctic, Arctic Circle versus political Arctic, and really it just comes down to the places that are cold and experience a lot of darkness. So what we mean by dark is, this is a picture from high noon. It was 11:59 a.m. In December 2017. So that's me driving at about 60 miles an hour on a snow machine. But the sun was nowhere near the horizon. We had a little bit of twilight to work with. That's the yellow glow you see in the sky. But this is as bright as it gets during much of the winter there. The sun sets sometime in October and it doesn't rise again until February. On the other hand, we're also dealing with places where you go for months at a time where the sun never sets. It'll dip low in the northern part of the sky, but it'll be up for months at a time. And this creates an environment and creates a climate system that operates very differently than what we're used to. It is, to say the least, cold, with average daily highs in the summer topping around the low to mid 40s, average daily highs in much of the winter being well below 0 Fahrenheit. In case you thought Williams was cold, this is the same weather data for Williamstown, with average daily highs in the summer hitting the high to mid, or the mid 80s, average daily highs in the winter usually in the 40s. So we're talking about a very different world, a very different climate, somewhere that seasons, as we tend to think about them, are really shifted from what we're used to here. Summer is a time that you might be wearing 1 jacket instead of 3. Winter is a time that you need to prepare to go outside. You might not be able to start a vehicle because it's so cold. And part of this is that the Arctic Ocean is really cold too. So I've drawn on here the water temperature from the Jersey Shore this summer and from Cape Cod. And for comparison, if you think swimming at the Cape is cold, this black line is our Arctic Ocean water temperature. So we're dealing with ocean water that's right around the freezing point, right around 0 degrees Celsius or 32 Fahrenheit. And it'll warm up by a few degrees in the summer, cool down by a few degrees in the winter, but it's pretty cold pretty consistently. And what that means is that the ocean surface freezes over. So I know you all have experience with Williamstown. You're used to this environment. So if you imagine what happens when a puddle freezes over, you get that thin skim of ice on the top. Imagine that puddle if it were 300 meters deep, so far exceeding the tallest building on campus a couple times over, and stretched from campus to Vermont. That is the Arctic Ocean covered in sea ice. You've got a thin skim of ice on the surface and a lot of water underneath. And so we end up with this drifting sheet of ice, that kind of fractures and these little bits of ice float around. These little bits of ice can be 4 to 6 feet thick, but it's still a really thin skim of ice on the surface of the Arctic Ocean. So this is what we call sea ice. It's just frozen ocean surface. Sea ice is different than glaciers or icebergs. So glaciers, for what it's worth, are accumulated snow on land that can then flow downhill. When pieces of glaciers fall off, that's an iceberg, as opposed to a piece of sea ice, which is called an ice floe. And so where my interest in the Arctic really comes in is in this era of climate change. In anthropogenic climate change, or CO2 forcings on the atmosphere, the influence of CO2 on the atmosphere, what it does when we emit CO2, we burn fossil fuels, is we increase the ability of the atmosphere to absorb electromagnetic radiation. And this radiation is naturally emitted by everything that has a temperature. So you are, in some sense, glowing. Our eyes are just not tuned to be able to see it. So the Earth is glowing, mostly in the infrared range. So if you were to use night vision goggles, this is exactly what you're seeing. And CO2 in the atmosphere can absorb that radiation. It warms up like a black t-shirt on a hot sunny day. It warms the air around it, which then can radiate more energy, keep more of that energy kind of being passed back and forth between the atmosphere and the Earth's surface. So this is what we mean by the greenhouse effect, where CO2 in the atmosphere is just able to absorb a little bit more to warm up the air, and the air in turn then warms up the surface and keeps everything at a higher temperature. So we've known for 150 years or so that climate change, or that CO2 can have this effect in the atmosphere. It's been well studied, well established, and anthropogenic climate change, that is human released CO2, has caused an average of about 0.7 degrees Celsius of warming around the world. It's a little bit over a degree Fahrenheit. Since the pre-industrial era. So since what we use is basically like the 1850s to 1890s as our baseline. That being kind of as old as we can get reliable temperature measurements for, because before then the glass blowing technology wasn't good enough. So if we were to take out human influence, we can calculate exactly how much the Earth would have warmed by now, and that amount is 0. We would have had a few big earthquakes, big volcanic eruptions that actually would have cooled things a little bit. Instead, we're dumping a whole bunch of CO2 into the atmosphere, and warming things up rather spectacularly. 0.7 degrees doesn't seem like a whole lot until you recognize that this is not the same number everywhere. And what we see is that climate change is really accelerated in the Arctic. We call this phenomenon Arctic amplification. And it's this idea that climate is changing fastest in the places where snow and ice are a key component of the local environment. Snow and ice are white, they're very reflective. And so the sun's energy as it's coming down gets reflected back up, and doesn't get absorbed into the surface, where it can turn into that kind of radiative energy, that heat that's being radiated out of the surface and then can be absorbed by CO2. So where we have a bunch of snow cover, it kind of keeps things cool, keeps things from warming up. You change the amount of snow cover, you change the amount of absorption, things warm up more, and then you melt more snow. So there's this dangerous feedback cycle that happens in these places where ice and snow are really important. And one of the places that that's most significant is in the Arctic Ocean, where you've got all of this sea ice, this frozen ocean surface, right up against water that's at the freezing point. So if you're used to putting a couple ice cubes in a glass of water, you see how they slowly melt. And while they're melting, the water right around them stays at that freezing point. This is something that we learned about in elementary school science classes. I imagine it's probably been a few years since we've done that, but things, when you have both ice and liquid water, will stay in a thermal equilibrium. They will keep each other cold. Where you get a little bit of warming, that just melts a bunch of ice. Where you get a little bit of cooling, you form more ice. And so the human-induced climate change, this anthropogenic climate change, really accelerates in these places where you have effectively a giant bucket of ice water. And we see that especially in the summer in the Arctic. So climate change has caused a 40% reduction in summer sea ice cover since the 1980s. And so this is an area that is not quite the size of Greenland, but pretty close to it. Roughly the size of Alaska in terms of total area loss. No, this is not a video anymore. Anyways, so with this loss of sea ice, what we're seeing really is that this loss happens in the summer. Every winter, our ice cover over this ocean kind of grows back out, responding to a really cold atmosphere, and so you've got heat that leaves the ocean and results in freezing at the surface. So I have a question in the chat box about why Antarctica has not experienced that same degree of temperature increase. You'll notice here that Antarctica in many places is actually cooling rather than warming. And this has to do with two things. First, there are some patterns to atmospheric circulation that have gotten a little wonky as some places have warmed more than others. Things like the jet stream have moved a little bit, and so you end up with colder air that has access to different parts of the planet than they used to. The other thing is that Antarctica is covered in glaciers instead of sea ice. Because you have the continent right there, you have this massive, and by massive I can't begin to describe how staggeringly huge this pile of ice is, that keeps things cold. So if you melt a little bit of the surface of Antarctica, you still have a nice white reflective icy surface. You would have to melt kilometers thick ice in order to get down to rock that's going to change how reflective the surface is. Whereas the Arctic, you melt a little bit of sea ice, melt say 4 feet of sea ice, that's done nothing in the Antarctic, but you're suddenly down to open water. You've changed the characteristic of the surface entirely. So a lot more sunlight can get absorbed. So a lot more additional warming can happen. So the Arctic is in this very delicate feedback cycle. The Antarctic is just a massive, massive block of ice. And so we don't see a lot of changes except for this map kind of cuts it off, but there's one little section of Antarctica where there's been some significant warming, where there's concerns about a few glaciers collapsing. But for the most part, just because it's continental ice, because it's glacial ice, it's a little bit more secure than the Arctic is. So this would be a nice video that shows how the sea ice extends out and melts back every season. You get this kind of seasonal cycle. The other thing that happens is because you have this really thin ice on top of an ocean, is that ice drifts around. You have a lot of movement, a lot of drifting of the ice that's in response to ocean circulation and ocean currents, and then the wind at the surface. So you can imagine this little ice being blown across like you would have with a toy boat on a pond. The problem is that, well, the ice in the middle, what we call the pack ice, moves a lot. Shore does not. So coastlines are fixed. This should not be a surprise to anyone, but where this drifting ice and the coastlines interact, you get some really interesting things happening. They can be kind of catastrophic. So where you have the fixed shore, you've got drifting pack ice that runs into ice that's maybe frozen to that shoreline. You can get these big ridges that form up to about 20 meters thick. 20 meters, that's about 60 feet. That's a lot of ice to pile up. And the way this happens is if you have an ice flow, a drifting piece of sea ice that is 500 by 400 meters and 1 meter thick, that's a pretty cute little small ice flow by Arctic Ocean standards. And it's drifting at 15 centimeters per second, or about 1/3 of a mile an hour, which is totally normal drift speeds. That ice flow, just because of the amount of mass that's in that ice, has the same amount of momentum as a jumbo jet taking off. So you can imagine if we're trying to send that much energy, even very slowly, but that much energy careening towards the coastline, when it hits other ice that's fixed, that's not going to move, that's where you get these massive ridges, these really big crashes that end up with these jumbles of broken ice piling up. And there was a question earlier about, is sea ice salty? Yes, it is salty. It's less salty than the ocean water that it forms out of. We'll come back to that later when we talk about measurement. But it is a little bit salty, and that makes it a little bit less strong than freshwater ice. So on a lake, you can pretty safely walk on a lake with about 2.5 to 3 inches of ice. It seems terrifying. People don't tend to go out and try it when I say it, but you can. It only takes about 4.5 to 5 inches of ice to be able to actually drive a truck on a lake. You want to do this slowly. You can break the ice if you're not careful, but that's how much ice it takes to actually support your weight. With sea ice, you need about twice that much in order to support, because the salt in there kind of weakens it. And so that contributes to some of the massive ridging and the big fractures that happen. So where we end up with these big ice ridges, you can get ridges that extend all the way down to the seafloor. And so we're pretty close to shore. It's fairly shallow water at this point. And so when you can anchor ice in with that ridge, the ice that's then frozen shoreward of it is protected. It's protected from the pack ice, and it's protected from being kind of broken off because it has this really big, strong anchor holding it in. And so that shore fast ice, or ice that's inward of the ridges, is a really important part of the local subsistence hunting lifestyle. So many of the communities that are out in the Arctic in these areas are fully separated from the road system, and for the most part, the kind of lower 48 style food system. And where a lot of food comes from then is hunting. It's hunting for seals, for whales in the traditions of these indigenous communities. But in order to do that, they have to be able to get on the ice. They have to be able to get on the ice that's not liable to then go drift out to sea. And that's where the shore-fast ice can be really important to the people who live nearby. The other thing that the shore-fast ice does is it protects the shoreline from storms. So this was a picture from a couple of years ago where there was a storm slightly offshore and we were getting 12-foot high slush waves. So you can see that these waves are kind of whitish. It has the consistency of roughly what you get out of like a slushy machine at a gas station, but in the form of really enormous waves. And so these storms offshore, if there's no shore-fast ice there to protect the coastline, can lead to some really severe erosion. So the coast itself is soil that's frozen together with ice, and you combine a big storm and this kind of delicate, not rock material, and you end up with large chunks of the shoreline falling into the water. So there are a number of communities that have built up protections using giant sandbags and other approaches, but for the most part, we're seeing just staggering rates of coastal erosion. So one of my thesis students this year, Matt Weisman, was doing a project measuring coastal erosion rates near communities. And there are places where we're seeing up to 18 meters per year. So that's about 50 something feet of erosion coming in from the coastline every year. For at this point, we're seeing that for about 15 years. So it's an enormous amount of Alaska that's fallen into the water because of degradation in the sea ice near shore. So I'm going to pause here for a second. If there are any other questions on sea ice, on climate system, on how that's playing out together before we get into what we're doing about this and how we're making these measurements. So if you have any questions, I'll pause for about 30 seconds to throw them in the Q&A box. And to a question that came up in the chat earlier, I'd be happy to talk more kind of at the end of this about general evidence of climate change and point you to some really great resources in case you have any relatives who need convincing. So to keep moving, I don't see anything showing up in the Q&A yet. My research and what I'm doing with students at Williams is really around this question of how do we make observations in this kind of environment. It's dark, so we can't use solar panels to power anything. It is windy and snowy and cold, and everything breaks, and duct tape doesn't work because it's too cold for most of the year. And what do we do? How do we solve problems in this kind of environment? And the first thing that I'm going to dive into that gets back to this is ice salty question was a project that was really looking at the implications of water around the coastlines on the climate system. And so we were interested in this for very big picture reasons. Sea ice in many ways acts as kind of a temperature control on the climate system of the planet as a whole. And so for getting the numbers that go into the mathematical models that we use to make projections about what might happen in the future, the very small scale behavior of sea ice has a really outsized influence. So when sea ice forms, you have little pieces of ice that push the salt around it out as the ice crystal itself grows. Water does not want to have a lot of inclusions, and so it pushes these little bits of salt out. And these little salt bits join at the edges to form these little pockets of really salty water. And these brine pockets can have influences on the material properties of the ice, which changes how heat flows through the ice. And so what we were wondering is if we're in coastal environments where the amount of fresh water changes a lot, if we're near rivers or anything, or creeks that are flowing out, how is this going to change the sea ice around it? And does that actually matter for our understanding of how sea ice responds to a changing climate? The problem is that freeze up season can be pretty rough. So we're already talking about cold, dark, but where you have any amount of wind, you get sea ice that forms in what we call pancakes. So these are tiny ice flows. They're usually a few meters to maybe 10 meters on a side, and 10 to 50 centimeters thick. They'll jostle around with the wind in the waves and eventually freeze over into sheets of ice. Calling them pancakes makes them sound very friendly. By mass, these are roughly Ford expeditions. So you can imagine if these are jostling around, that they could do a whole lot of damage to something. I don't know if anybody has tried packing a wave tank with Ford expeditions, but I would not recommend it. And so we were trying to measure these centimeter, millimeter scale processes in the ice in this environment. So what we ended up doing was building a buoy and then reinforcing it like crazy. So we called this frame that we put around our instrument the shark cage. It is steel or aluminum stair grating. That was what we calculated was the kind of necessary amount of force that these this buoy system would have to be able to withstand. And so as we bolt on the stair grating, bolt on the shark cage, we freeze this buoy into the ice. So this first image is from October, the second image is from March, and we let the ice then, to put the buoy in the water and let the ice grow around it so we can measure the growth processes in the ice. We did have one issue, which is that an ice flow ran over one of our buoys. So we had to go back up in December. And we, fortunately, with a metal detector, were able to find the buoy. But we did ultimately have to chip out about 1,000 pounds of ice in order to be able to extract the buoy, get it back to floating, and actually get some data with it. So this was me. It was about -10 Fahrenheit that day. Turns out the biggest down coat I own is quite comfortable for working out in when you're chipping that much ice at that temperature. We used every tool available to us, including a number of pasta colanders for extracting that. But then we got it back to operating, back to working, back to upright. We're at recorded data for the rest of the season with only a few broken instruments on there. We did ultimately, when we were recovering the buoy, chainsaw it out of the ice. This is one of the most exciting instrument recovery missions I've been on, where I just had a couple of electric chainsaws cut through the ice right underneath your feet, and as long as you don't cut more than 4 feet down, you're fine. What we measured in this process, actually far more interesting than the changes in the ice itself, is that the water underneath the ice got a whole lot saltier over the course of the winter. And this makes sense in retrospect. You've got, you're not getting any extra rain flowing in, you're not getting any river discharge at that point in the year. And then the ice itself, as it freezes, it's kicking out a little bit of the salt that was in the water that's being frozen in. And so we go from salinity levels of about 18 parts per thousand, which is barely qualifying as salt water, to well past the kind of standard ocean of 35 parts per thousand and up to levels of about 70 parts per thousand. So we end up with this extra icy water. Water temperatures drop underneath because the freezing point is going down. And what we find is that this changes the amount of total heat transport through the ice. And the ice through this process is actually better at insulating the atmosphere from the relatively warm ocean. But this is all well and good for the climate models, but it turns out things like this really don't actually matter to the people who live in these environments. So a lot of the work that I've done has happened out of the community of Keagvik, Alaska. So it was formerly known as Barrow before they changed it back to their original name rather than the colonial name. But this is the northernmost community in Alaska. It's got about 2,000 people. It's a regional hub, which qualifies as as the city. But you cannot drive to it. You can fly on Alaska Air or Raven Air, and there's very limited in and out of these communities. So what we got into here was that there are a lot of questions that are very relevant to understanding how sea ice works. But in order to get there, you actually have to talk to the people who live next to the sea ice and understand what they know and understand and what they don't. And so this is a project that's really gotten a foothold here at Williams with students. And it's taking these big databases of community observation. So you have a bunch of people in these towns that are working out on the ice, that are hunting and fishing and spending all this time outside, and understand how the ice works really well. And so they're logging ice conditions and have been since about 2006. And so now we have enough data that we can start taking some of these quote big data approaches and digging into what they can tell us about how the ice is working. So this is a map of Alaska. Barrow is up here, or Utqiagvik is up here. Latitude is about 71.5, almost 72. And we have, these color bars are showing how many observations we have from these different communities. And we're able to start piecing together, especially for Barrow and Wales, there's enough observations and enough data that we've collected to be able to put this into a longer term context. So we can start looking at when sea ice is growing and stabilizing. What we're finding is that we're trending earlier in the year for the first initial growth of ice, but that we're also getting more times that it covers over with ice and then is open water again, and covers over and is open water again, which makes for a longer period of instability and uncertainty, kind of at both ends of the season, where we're getting that both in the early season and the late season. One thing that really came up in these discussions with community members is that the ice near shore, when it breaks out quite suddenly, that can be really devastating if you have anything out on the ice past that. And so sometimes there'll be setups for seal hunting. And so what we're trying to understand is kind of what are the conditions around which these ice breakouts happen. And so if you imagine one of these big chunks of ice kind of cracks and drifts away from shore, we're talking about areas that are maybe 10 to 40 kilometers across and many, many times that long. You're thinking about like Puerto Rico of ice drifts away. And if your hunting equipment happens to go with it, you're likely never to see that again. And so we can start looking at community records of these breakout events and piece together frequencies and kind of what times of year we're likely to see problems and what conditions set up for these breakout events. So we've been looking at certain wind patterns as we can look at certain wind patterns in these environments. We can look at different ways that the ice motion around it can then be a predictor of when ice is going to break out and break free. So the kind of flip side to breakout are these ridging events, when you have the pack ice collides and builds up these nice thick ridges. So much of the winter, it's going to be dark, it's going to be cold. This might be several kilometers offshore that this is happening. And all of this time, it's not safe to drive out on the ice. You can't drive out on unknown ice conditions in case one of those breakout events happens and suddenly you're adrift in the Arctic Ocean. Also, this is an area that has a lot of polar bears, in addition to walrus, various types of seals, some limited Arctic char in the summer, but mostly like the main wildlife, at least in the winter here, is going to be polar bears. And the coastal environment really does rely on this shelf ice, or this stable shore-fast ice as a means of getting around. But you can't necessarily tell from above what's underneath one of these ridges. So these little piles of ice out here, they could be 3 feet thick. It could be just like one shard of fractured ice that ends up on top, or it could be the top of a 10-foot deep ridge of ice. And you really just have no way of knowing from above without somehow getting a measurement underneath the ice. And so that spun off this other new project that's looking at the seismic detection of ridging. So seismic sensors are sensors that we embed in the ground and they detect shaking. And so this shaking can come from earthquakes, can come from vehicles. And what we're really interested in is the collisions of pack ice and shore ice offshore. And when you have airplane-sized amounts of momentum colliding with the shore ice, you have conditions in which we expect that there's going to be enough seismic energy generated, enough shaking that even though this is happening all floating in the ocean, you'll be able to feel it on land. Maybe not a person feel it, but at least these instruments will be able to. For what it's worth, these sensors look really boring. You've got your little like shack of batteries connected to a drill down into the permafrost or the frozen soil that anchors the instrument in place, so you can measure really precisely what the shaking is happening. And so with these ridging events, what we see is when we have a big piece of ice, of pack ice, collide with the shore ice, we get a loud noise. If we look at this in what we call frequency space, so if we measure how much energy there is at different wavelengths, or effectively different sounds or pitches, this is exactly what happens with sound. It's just like outside the range of human hearing. It's too low. Ridging events are loud, especially at the higher frequencies. And so in this diagram, we know from radar footage here that ridging started right around 12 noon. And you can see that this is when things just like get a little bit noisier across all of these frequencies. So the yellow is louder, the blue is quieter, and we can pick up that this is happening using the seismic instruments nearby. For what it's worth, our imaginary 500 by 400 meter ice flow from earlier is this big. So often what we're dealing with are ice flows that are many hundreds of times that size. If that ice flow has the momentum of a 747, then this ice flow, the pack ice that's near it, is going to be United's entire fleet. So where we're at with this project is that we can use the particular characteristics of what these collisions sound like in order to diagnose or tell exactly what kind of noise something is. So there are other things that create noise, create seismic noise. Earthquakes, wind shaking buildings will create seismic noise. Human activity can create a lot of noise. And so what we've done with the students in my group have watched a lot of this radar footage, found ridging events, and then in the frequency space, what we find is that there's particular ratios of frequencies that tell you when something is actually a ridging event. We found that it needs to be louder at certain higher frequencies, quieter at lower frequencies, but then louder at high frequencies and louder at these mid frequencies. And if you kind of space these out, you can find characteristics that will be a good indicator that a particular event is ridging and can tell you what's happening offshore. And so now what we're doing is working to expand these seismic monitoring stations into communities that don't have the really big instruments. So this one instrument that we've been working with is a $40,000, $50,000 instrument. What we're doing instead is getting these Raspberry Shakes. It's actually, there's a Williams alum who works with this company. But we're getting Raspberry Shakes, and we are sending them out to rural communities in Alaska to have them installed in the permafrost kind of ice cellars that they use to preserve meat over winter. And where these big instruments are great for giving us really detailed information that we kind of that we can use to round out our understanding of how the seismic properties of these systems work. We know we need to see this in more places. We know we need community observations to pull that piece back in. And we know we need to be able to answer the questions that actually matter to the people in these communities. So as we're getting this work spun up, as we're developing these partnerships with local communities and their subsistence practices, and being able to do science that both informs their day-to-day life and meets the needs of the broader climate community, and helping understand how this shorefast ice behaves in response to climate change. So the last thing I want to do on this this particular topic is give a plug to my thesis student, Marshall, who at the moment is still looking for a job since his fellowship required travel. So if anyone wants to hire Marshall, go for it. But otherwise, I'm going to wrap up here. I hope you have enjoyed this kind of tour of new sensing technologies in the Arctic. It's a weird space to be operating in to study climate science, since many of the tools that we normally use don't necessarily work. A solar panel is not going to do you anything for 6 months of the year. But we have a lot of opportunities, a lot of ways to leverage what exists in these environments, and a lot of ways to leverage new technologies to get information about systems that are changing quite quickly. So I would once again encourage you to please use the Q&A box, and I'll happily take any questions. So we have a question in the box. What legislative policies would advance our work? One of the big things is steady and secure funding for research. Especially climate research is and has been a political football for a number of years. Especially, I'm gonna say like 5 years ago, NASA's budget was cut by exactly the amount of their climate research program. NASA being one of the biggest funders of research in this environment. So legislative policies that would really help would be steady and secure funding for the National Science Foundation and NASA. Also funding that would help Native and Indigenous communities be able to run their own research programs. There's a huge amount of capacity and understanding of how these systems work, and we really need to be able to support Indigenous scholars and subsistence hunters in being able to translate their knowledge into settings that we can use for other purposes. There's a huge amount of opportunity here, and it's a really underutilized resource, largely because there aren't mechanisms for there just aren't mechanisms for getting this information across these kind of system borders. So there's a question, does the ridging activity affect the fish and wildlife? The shore-fast ice, that is the really secure ice behind the ridges, that is really necessary for certain species. There are seals that rely on being able to kind of get back to the same holes a few times. How it affects fish and wildlife differs along the Alaska coastline. It's really a pretty, it's a long ways of coastline where we're dealing with things like this. And the species involved really depend from place to place. There are a number of different ways that this can affect fish and wildlife. Walrus is a really big one that need these shore-fast ice areas to haul out. The ridging activity itself, like while it's happening, not so much, except that polar bears do tend to build dens in the ridges that form there. So I hope that's kind of answered your question. I'm not a biologist, so my knowledge of the Arctic fish and wildlife is mostly because they're cute and giant and fuzzy, and not so much because it's my particular area of expertise. So there's a question, with further global warming, what would we predict to happen with respect to conditions in the Arctic? At this point, we are expecting that by the middle of the century, we will have largely ice-free summers in the Arctic. That is, sea ice will be down to just isolated drifting flows. We won't have large areas of sea ice in the Central Arctic anymore. Fortunately, sea ice is a pretty resilient system in that if we can reverse climate change, if we can keep it to less than 2 degrees C, sea ice responds quite quickly and will come back. And we'll still freeze over every winter. It'll just be thin, it'll be very transient, it'll move a lot more. So we really don't know yet what this is going to do to coastal ice, whether a thinner, more mobile pack ice will mean more ridging, more stable ice that could then last longer. We really just have, we've got a lot of kind of open questions. We have a lot more research to do in the meantime. So there's a question, how does training the communities to use the Raspberry Shakes work? We're figuring that out. As it stands, we were intending to be up there this summer, working with these communities hands-on, but with COVID and communities largely not having a lot of healthcare infrastructure, they've more or less closed to outside. You can't fly into many of them anymore unless you're a healthcare provider. So we are working on getting a remote training program up and running, but it's been a lot of reinventing things that we didn't really expect to need to do. So there is a question, has the climate in Williamstown changed in the last 100 years, and how do we predict it'll change in the next 50? So this is actually a question that I might redirect to my introduction to weather and climate class. And so we do study, Williamstown has phenomenally great climate records. We have temperature, snowfall records, rainfall records going back 100 years. Because of the data collection at Hopkins Forest, we have just a really tremendous amount of resources available to us. That said, the climate in Williamstown has not changed very much. Our weather has gotten more variable. We have more warm spells in the winter, but then also more cold snaps. And it's just more variable. The actual mean temperatures haven't changed more than a few, like a small fraction of a degree. But we are seeing kind of more shorter lived periods of either cold weather or hot weather. and really that's kind of what we expect for the next 50 years as well. Williamstown and most of kind of northern New England is in one of the places in the world that's going to be least impacted by climate change. It's very ununiform, the impacts of climate in various places. We see it really accelerated in the Arctic. In New England, we're not going to see a lot of changes. It might get a little bit warmer. We might get a few more storms, but altogether, we're really one of the winners of climate change. And that puts the moral obligation on us to A, do something about it, and B, support those who are in places that don't have those resources. There are a couple questions related to climate change experiments and resources. There are a ton of resources on the internet. I cannot point you to all of them, though if you want to email me afterwards, my email address is right here. I'm happy to give you some pointers. But the National Oceanographic and Atmospheric Administration, NOAA, has a big resource team or big education team that's developing climate change experiments and things. I can give you instructions for one of the labs that we do in Intro to Weather and Climate, where you do actually create CO2-driven climate change in a 2-liter soda bottle. You just need an infrared lizard warming lamp to do it. So please, if you have questions about climate education resources, please email me. I'd be happy to either connect you or send you some materials. And then there's one other question, do we run winter study programs to the Arctic? At the moment, no winter studies, but we do have plans that are slightly on the table at the moment of running a travel course for a geoscience senior seminar. We're scheduled to go to Alaska for spring break this year with students in the class. We dig snow pits with the avalanche forecasting centers around Anchorage, go out in the Matanuska Glacier, go into the permafrost research tunnels in Fairbanks, and then go out on the sea ice in Utqiagvik. But that is all assuming that we are safe to travel in March, which at this point is out of my hands. And then I think, I'm not positive where I'm at on time, but if I'll answer this one last question. Advice for different arguments we can use to convince skeptics of anthropogenic global warming. This is hard. If we knew how to convince people, we would have done so by now. We would be in a very different place. The thing that has shown to work more than anything else is one-on-one conversations with people you care about. So people are generally not swayed by experts. There is a very pervasive in many aspects of American life right now distrust of experts, and that has been a problem. So talking to people you care about, talking to people who care about you and your understanding. There are no silver bullets for arguments. Some people can be swayed by the economic argument of, whether or not this was in like climate. Humans didn't try to cause climate change, at least not until the 90s, at which point we knew what we were doing and have continued on blindly since then. But this wasn't intentional. This was a byproduct of not understanding the implications of our actions. And so the way we really convince people to care and do something about climate change, you can set up the lizard lamps for climate in a bottle in front of them to watch it happen, but really it has to be understanding where they're coming from as a person, why they're skeptical, and treating the root causes. That said, like, there is mountains of evidence of climate change, and it's really just a matter of choice to disbelieve something that's right in front of you. So with that, I will wrap up and thank you.
Thank you so much, Professor Bradley. This was absolutely fascinating, and we really appreciate you taking the time out of your day to speak to us. And also want to thank everybody that showed up in the middle of the day today, more than 60 listeners. We are very grateful to everyone that's participated, and we hope to see you again at future talks in this series. Again, that's going to be Professor Wadsworth in a few weeks, and then Professor Roberts closing it out. You can keep up to date on the future events in the lecture series at alumni.williams.edu/virtual. I just posted that link into the chat. And we also hope to see you at future online and then hopefully in-person events organized by Williams Boston in the coming months. So thank you again, and I hope everybody enjoys their day. Thanks again, Dr. Bradley.